Alright, in this lesson we're going to look at the relationship between the normal distribution and the binomial distribution. So we have studied both of these distributions in the past, and we've used both of them as probability distributions. We spent all of unit 14 and 15 calculating the probability of binomial events and finding the distribution in some cases of events whose behavior was determined by binomial probabilities. And then just recently we have looked at using the normal distribution, which we had studied a long time ago in statistics, how we could interpret normal distribution in terms of as a probability distribution. Now there is a connection between these two things, and it applies in certain situations. So what we're going to learn here today is we're going to learn to recognize the situations where the normal distribution can be used to approximate the binomial distribution. We're going to find that for certain types of problems where it would be hard to find the probability using the binomial distribution, we can instead use the normal distribution, which is sometimes easier to apply. And of course we're going to use the normal approximation to determine the probability of binomial events. And of course keep in mind that this is only going to happen for certain types of problems or certain types of questions. Let's say certain questions, and it only applies in certain situations, because we're going to find that the normal approximation isn't always a good one. So what do I mean by using the normal approximation to the binomial distribution? All right, let's start by looking at a situation. Imagine taking a multiple choice test and randomly guessing on every single question. Okay, warning label on the side there says that you shouldn't do that. You should study, and so you know what's going on and you're not randomly guessing, but let's say you did. This situation is modeled by the binomial distribution, because each question can be thought of as an independent trial. There are n questions, so we have n repeated trials on our test. The probability of success, if we're randomly guessing, is the same on each question. And let's say we have 4 options for each question, so the probability of getting one right is 25%, or 1 in 4, or 0.25. So we can take this situation and we can figure out the probability distribution that models this using binomial theorem. So our probability distribution would look something like this. We can find the probability of getting 0 correct, or 1 correct, or 2 correct, or 3 correct. And you see here why you shouldn't just be randomly guessing. You're most likely to get actually just 1 correct here, and you only have about a 40% chance of getting 1 correct. So this is what our probability distribution from the binomial probability distribution looks like there on the left. Now, looking at this, you would say, okay, if this is a binomial distribution, which we have been studying, and this thing that I have over here on the right is a normal distribution, these two things look almost nothing alike. Let's try this again here. Okay, so for one thing, our normal distribution is, well, as we talked about in the last lesson, the normal distribution is continuous. And what that means is when we look at the graph of it, we see a nice smooth curve. Whereas if we're looking at our binomial distribution over here, binomial distribution, of course, is a discrete probability distribution. And when we look at the graph of the probability distribution, we can see that it is not smooth. So that's one major difference between these two. The other difference here is when we look at this binomial probability graph here, we see that it is not symmetric. This one here is skewed a little bit to it's a skew right distribution. And one of the key properties of the normal distribution is that it is a symmetric distribution. And most of the problems that we solve using the normal distribution rely on the fact that it is completely symmetric. So we've got these key differences between these two types of distributions that kind of imply that we can't just replace one with the other. But let's watch what happens when we change the number of questions on the test. So instead of having 5 questions, let's say we have 20 questions on our test. And we use the binomial distribution to calculate the probabilities. What we can see here is our binomial distribution is getting a little bit smoother, and the shape of the distribution is getting a little bit more symmetric. And if we increase the number of questions to something like 100, we've got something that looks reasonably symmetric and reasonably smooth. So the trend in what we've seen here is that as we increase the number of trials, or in this case the number of questions, or as n increases, and in this series of graphs n is increasing as we go from left to right, basically what we see is that our binomial distribution starts to resemble our normal distribution. Let's just say looks more like our normal distribution. Okay, so if we're thinking of using the normal distribution as an approximation to the binomial distribution, the key is that this approximation will only work in certain cases. And those certain cases are large n values. Okay, and I'll just put large here in quotation marks because we're going to talk about a specific criteria that lets you decide whether or not that that approximation is going to work. Okay, so here we go for a normal approximation to the binomial distribution. So let's say we have a binomial random variable where n is, well, the usual definition of n is the number of trials. P is, of course, the probability of success, whatever you decide a success is in the context of your binomial experiment. The criteria for figuring out is if the normal approximation applies is if n times the probability of success is greater than 5 and n times 1 minus p, or 1 minus the probability of success, or q, the probability of failure, is also greater than 5. So what does NP represent here? NP, of course, is the expected value for our binomial distribution. So this is the expected number of successes. And over here, n1 minus p, or nq, of course, is the expected number of failures. So if the expected number of successes and the expected number of failures are both bigger than 5, then you can use the normal distribution to approximate the binomial distribution. Okay, so let's run back a little bit here and take a look at our 4 cases here, or 3 cases here. In our first one here, on the far left, if we calculate the expected number of successes, NP, we get 5 times 0.25. We just get a value of 1.25. So clearly, in this case, binomial distribution cannot be modeled by the normal distribution, and we could see that just by looking at the graph. This middle one here, if we calculate NP again we had 20 questions. The probability of success is still 0.25, not 0.025, but 0.25. Let's try that again. Then we get that the expected number of successes is exactly 5. So this is kind of the borderline case here. We wouldn't say that the normal approximation applies here because NP has to be greater than 5 and is exactly equal 5. But this is the point where our curve just starts to look like a normal distribution. And of course, for this one on the right, we've got 100 times 0.25, 25, which is clearly greater than 5. So this is one here. Definitely the normal approximation is going to apply, and we have a nice looking normal shaped curve up there. Okay, and in this case we only have to calculate the number of successes because we know the number of failures is going to be larger than the number of successes because the probability of failure is 0.75 or 3 times as big. Okay, so if you've gone through that and you've calculated the expected number of successes, the expected number of failures, so you know that the normal distribution applies, the normal approximation applies, then our binomial variable can be approximated by a normal distribution, and we can figure out the properties of that normal distribution. That normal distribution will have a mean of, given by n times p, or the expected value, and it'll have a standard deviation given by, standard deviation is the square root of np times 1 minus p, or npq. Okay? So if you know n and p, you can figure out the mean and the standard deviation, and then you can turn your binomial probability question into a normal probability question. So let's look at an example here. So Z-Cola, a soft drink company, has a 42% market share in Hamilton. Their marketing department conducts a blind taste test of 70 people at Lime Ridge Mall. How many do we expect to choose Z-Cola? Okay, so this here is just asking us for the probability of success in our binomial experiment. Why is this a binomial experiment? Well, let's think about what's going on here. We have multiple taste tests that we're doing. We're doing 70 taste tests here. So each taste test is one trial in our binomial experiment. These trials are all independent from each other because they're being done on different people. So we've got n equals 70 here. And we can figure out something that we have two possibilities in each one. We have success and failure. So we could say that success is that they choose Z-Cola. And of course, a failure would be that they don't. So what is the probability of success here? Now, this isn't a perfect sort of question here because they tell us that it has 42% market share. That means that 42% of the soft drinks sold in Hamilton are Z-Cola. So it's not really the same as the number of people that like Z-Cola, but we can use that 0.42, that 42%, as the probability of somebody liking Z-Cola. And of course, Q is going to be 1 minus 0.42, 0.58 for the probability of failure. Okay, so what is the expected number of people to choose Z-Cola? Well, we know from our binomial distribution, the expected value of our random variable is going to be NP, which is 70 trials times 0.42 is our probability of success. So we're going to expect 29.4 people to choose Z-Cola. Now, what if you do this experiment and you have exactly 25 people choosing Z-Cola? That's what part B is asking us. What is the probability that exactly 25 people are going to choose Z-Cola? Well, here they're asking for sort of a single probability, or the probability of a single value. This is the kind of question where you want to go and just use the binomial distribution that you are so comfortable with, having practiced it all in that past unit. Okay, so we know that, let's see, we're interested, K is going to be 25 because we're interested in the probability of getting 25 people. We know that our binomial probability is the probability of K is N choose K, PK, Q, and minus K. So what we want here is we want the probability of exactly 25 successes. So we're going to have 70 choose 25. Our probability of success here is 0.42. Our K value is 25. Our Q value is 0.58. And we want 45 failures. And we can work this all out, and we get 0.0566, or 5.6%. Okay, so there's a 5.6% chance, 5.6% chance that exactly 25 people in our taste test will choose E. coli. Okay, now let's look at the third question here. What is the probability that fewer than 25 people will choose E. coli? Well, if we're asked about what is the probability that fewer than 25 people will choose E. coli, then we're looking at a bunch of different probabilities, because we could be looking at, thinking of this in terms of the binomial distribution, we'd have to calculate the probability that 24 people choose it, or plus the probability that 23, plus the probability of 22 people. I mean, and so on and so on and so on, all the way down to the probability that 0 people will choose it. And we add these all up, and that would give us the probability that we're looking at. Okay, that's going to be a long, tedious process. Okay, so the binomial distribution, it's difficult, it's kind of tricky or complicated to calculate these probabilities when you are looking at the probability for a range of values. In this case, our range is everything from 0 up to 24. This is where you want to use the normal approximation, if possible. Okay, so the first step in using the normal approximation, let's number these, let's say this is number 1, is the approximation valid? Does it apply in this case? Okay, so first thing we have to check is the value of NP. So our N value was 70, our P value is 0.42. We've got, that gives us, that's our expected value again, 29.5. This is greater than 5, so far so good. Then we also have to check N times 1 minus P. So 70 times, what was that, 0.58 is our probability of failure. It's a multiplication in there, just to make that clear. We get 40.6, which is also greater than 5. Okay, just fix that. So it's also greater than 5, so both of these things are true, so therefore we can use the approximation. We'll just say can use. Okay, so how do we actually use the normal approximation of the binomial distribution? Well, let's give ourselves a little bit more room here. First thing we want to do is let's find the values of our mean and standard deviation. Okay, so using the formula that we had before, our mean value is just going to be NP, just that expectation value, 29.4. We've calculated that a few times. Standard deviation is going to be the square root of NP1 minus P, which in this case is going to be the square root of 70 times 0.42 times 0.58. So our standard deviation here is going to be 4.13. Okay, now what is the probability that we want. We want the probability of x less than 25. Okay. Now, this was for our discrete. This is our discrete probability. Okay. Now, we have to do something slightly different because our normal distribution is a continuous probability distribution. So the difference is kind of illustrated over here on the right hand side. So I've got my my binomial, my discrete probability distribution here. If we're using the normal approximation, it's going to look something like this, and then have a peek over here and do something like that. Okay, so if we just did what the probability that we want here is, we want everything less than 25. So we don't want 25 here, but we want everything here, and we want here, and we want here, and we want here. So we want all of this region kind of shaded in blue. Okay, but if 24 is sort of right here at this dot right there, using 24 as our value is going to leave off all of this stuff on the right hand side. Like all this stuff right in here is going to be left out. And if we use 25 as our value, we're going to include all of this stuff here that we don't want to include. So what we do is we choose a boundary in between there that is going to include all the stuff in 24 but none of the stuff in 25. So that value is going to be halfway between 24 and 25. So we want the probability of x less than 24.5 for our continuous distribution. So what this problem looks like now is it's a normal distribution problem. We've got a mean down here of 29.4. We've got some standard deviation. We have some value here, which is 24.5. We want to find all of this area in here underneath our normal distribution curve. So how do we find probabilities using the normal distribution? We're going to set up our z-score. So we want z for 24.5. So we're going to subtract off our mean, 29.4, divided by our standard deviation, 4.13. We get a z-score of negative 1.186. So we'll round that to negative 1.19. So we are negative 1.19 or 1.19 sigma below the mean, which makes sense with our diagram that we have over there. We look up that z-score in our table and we get an area of 0.3830. That of course is the area from the value to the mean, so that's this area in here, 3830. So the area that we want is, I'll just call it the total. We want 0.5 minus 0.3850, which is going to be 0.117. Okay? And that's going to be our probability. So therefore, let's round it up. Let's say that there's about a 12% probability that fewer than, and we want to go back to the original discrete number, 25 people choose Z-cola.